Good afternoon to all of you. This is the Smart Grid Educational Series webinar for February 2013. This is Irfan Ibrahim of the Bit Bazaar, as well as from Citer Energy. Citer Corporation is a large integrator in the United States, and I am leading their energy sector practice. And this Smart Grid Educational Series is now coming under the Citer Energy practice. This afternoon, we are very privileged to have three amazing contributors to our industry in Barry, and correct my pronunciation of your name, is it Haaser?
Barry Haaser, that's right.
Okay. And Rolf Bienert and Chris Cotting. And they are going to be presenting. First, we're going to be hearing about Open ADR, the standard and an update, and the Alliance. And then we're going to hear about USNAP. So I just wanted to spend a couple of minutes to create a motivation for these presentations, and then I'll hand it over to Barry. The situation now in our industry with the centralized power slowly being decommissioned and moving to distributed energy resources that are intermittent is going to create challenges going forward in terms of the availability of electricity at certain times when the demand may be very high. This is why it is very important for us to enable demand response applications that can tailor the load so that it can follow the supply of electricity at certain times. This will allow deeper penetration of renewable energy, and it will also help reduce the carbon footprint while keeping the cost of electricity affordable. It is becoming increasingly more and more expensive to supply electricity during the peak periods because the utilization factor of those plants that provide that peak energy is very, very small, and yet the capital expenditure is there. So having a good effective demand response application across the North America and eventually across the whole world will be very helpful for utilities that are providing electricity to customers so that customers can continue to live life comfortably, safely, reliably, while the utility can deliver electricity in that just-in-time system. As you know, storage is very expensive, so the just-in-time network is the way we make it work as much as possible. And having a standardized way of providing demand response signals to customer premises, whether it be industrial, commercial, or residential, is going to be very important. The Open ADR is an attempt to do just that, is to provide a set of standard signals from, whether it's from a utility, like an independent service operator, it could be from a distribution company, it could be from an aggregator, or any other third party. So we're going to hear a presentation on Open ADR standard, which has been developed in an industry in a very collaborative manner. The other presentation has to do with the USNAP, and this is an attempt to provide a standardized interface for smart devices. And the reason why this is so important is that the development of smart devices is occurring at a different pace than the development of the protocols for home area networks and business area networks and so on. So having a standardized interface on devices allows the manufacturers of these products to develop their products, provide certain standardized services for smart energy, and not worry about how the protocols in those networks are evolving. So the USNAP is an attempt to create such a standardized interface. Why is this important? Because the more devices that are plugged in to the smart infrastructure, the more granular control we will have on the demand for electricity, and therefore we can tailor the load to follow the supply of electricity, as I was mentioning in the earlier part of my comments. So having a standardized interface means many, many vendors can participate and allow the protocols to evolve at their own pace. So with this background and motivation, I now welcome the Managing Director of OpenADR, Barry Haaser, to tell us a little bit about OpenADR and then pass it on to Rolf and others for the rest of the presentations. Barry, the floor is yours.
Thank you, Irfan. Welcome, everyone. We're delighted that you could carve out a little time out of your day today to join us to hear about two important emerging standards. First, we'd like to share information about OpenADR. Irfan, but I'm not seeing the slides.
Yes, so I'm going to pass the ball to you, and then you'll be the presenter.
I got it. Okay.
Yes. So just give me 1 second, and I will do just that.
All right, it looks like it's up. So what we'd like to start with today is a presentation on OpenADR, Open Automated Demand Response, and we'll specifically focus on enabling automated demand response worldwide.
The horizontal arrows at the top is how you move the slides.
There we go. Okay. Thank you. So I think everybody's quite familiar with some of the challenges that we have in the grid. We have a number of supply factors coming into the grid that makes balancing the grid extremely difficult. We've got intermittent sources of power from wind and solar. We have different peaks and availability of energy sources coming into the grid. And yet, through all this, we're continuing to struggle with ways to forecast grid demand and how to best match that supply and demand in the marketplace. So the electric utility industry has, over the years, focused on first demand-side management and then demand response as a core technology for essentially shifting loads from a peak period to an off-peak period. And here we can see in green an area during the peak period from 12 to roughly 6 p.m. where we're trying to shift that demand into an off-peak period, typically 7, 8, or 9 o'clock in the evening. So this idea of shifting demand is pretty commonplace among energy-constrained markets. The concept of OpenADR, Open Automated Demand Response, emerged about 10 years ago after the California energy crisis during the last decade. So OpenADR is really a non-proprietary or standardized methodology for delivering price and event and grid status information from an energy service provider to a customer, which could be residential, commercial, industrial, using a standardized language, in our case, XML web services, over the internet. So it's a client-server relationship between the demand response service provider and the customer. Now, this model also supports a variety of use cases and models that we see in industry today, such as support for energy aggregators, system operators, utilities, and other players in the marketplace. So each transaction, each message that moves across the internet is sent in a secure way, and Rolf will elaborate on that in a few minutes. So OpenADR has been around for some time now. In its earliest incarnation, it was known as OpenADR 1.0 or just simply as OpenADR. And today, there are about 260 megawatts of controllable load installed worldwide based on the original OpenADR standard. And if we look at another map, you can see that there are deployments here in North America. So it's not just a California initiative. There are OpenADR deployments throughout North America, in Europe, and scattered throughout Asia, including Australia. So this is truly a global approach. Building on the initial OpenADR 1.0 profile specification, NIST, through the SGIP, started a harmonization project back in 2009 through the Priority Action Plan. Actually, there were 3 formed around this particular technology, 3, 4, and 9, PAPS 3, 4, and 9. And the idea here was to standardize on the price signals, the way the data is represented, and to come up with a standardized methodology so that we could establish true interoperability between servers and clients and avoid some of the pitfalls with the original 1.0 standard or specification in which the specification was open to interpretation from implementers. So if we look at its simplest form, basically what we're doing is establishing a pricing model, as you can see on the lower left quadrant. We determine what that price signal is going to be. We use the Open ADR messaging framework to capsulize that data. We move it over the internet through a secure fashion from a server to a client. And we'll talk about some of the models there between the relationship of clients and servers a little bit later. That goes to an end customer, again, residential, commercial, industrial, it doesn't matter, where the client then takes action based on that message, which could be either a price or an event-oriented message. And with that, I'm going to turn the ball over to Rolf Bienert, and he's going to take a little deeper dive into the technical elements of Open ADR.
Excellent. Thank you, Barry. Yeah, and I'll pick it up right where Barry left off. Basically, as Barry mentioned, we had these priority action plans from NIST and the SGIP. Oops, let me see if I can forward this.
I'm moving the privilege to you now.
Okay, gotcha. All right. So you should see those nice blue boxes there now. Perfect.
Yes, we do.
Excellent. Thank you, Irfan. Okay, yeah, so these priority action plans then worked on a common system for demand response and energy information exchange. And the work items were passed on to OASIS. And in fact, the OASIS Energy Interoperation Technical Committee picked up all these requirements, as you can see here, coming from OpenADR 1.0, other IRC requirements from NASB, other requirements from the OpenADR use cases from the UCA, and of course the SIM model basics, and all of these were packaged together in the OASIS Energy Interoperation specification. Now, this specification is a very big, very large framework. So it's hard to really build a product with it. It's more a data model for all of this, and it has a lot of different facets for the different areas of the market. And so the OpenADR Alliance picked up those particular elements that we need, or that we felt we need for OpenADR profiles. And with that, we created the OpenADR 2.0 standard. Now, let's quickly look at some of the terminology in the energy interoperation. I know this is, in fact, a fairly confusing chart here, but the energy interoperation is fairly clear on the meaning. So in case you ever get a chance to look at that, you'll see this chart in there. It defines a virtual top node, which you could just say is a server. But really it is the entity behind the server. So it's not only the server software, if you will, that runs, say, at a utility or an ISO level. It is the utility itself that represents this virtual top node and can have multiple different programs, things like that, maybe even different actual servers that you connect to. So there can be a variety of architectures behind it. And then the virtual end node, in turn, is in fact a client to this previously mentioned server, to the VTN. But the same thing applies here, as I mentioned, for utilities. It might well be that, for instance, a larger facility forms one virtual end node, even though they have several buildings, maybe even in several different areas, jurisdictions, utility districts, and things like that. But all of them could be combined under one VEN if that is the desired architecture. Now, as you can see in the picture with all these nice blue dots, there is a great variety of communication architectures available. But one thing I want to mention here is that do not mistake this for a large network. So, for instance, a VTNA on the very left-hand side, in fact, I think I can probably take a pointer here, on the very left-hand side, does not directly communicate, say, with a client device, a VEN, on the right side here. So messages that are being exchanged between, say, A and B are completely terminated between these two entities here. Then the system in node B here, whatever that might be, maybe an aggregator, maybe a large building control system, makes their own decisions on which of their resources they should deploy in order to satisfy the request coming from A to B. So B creates essentially its own messages with its own addressing, with its own content and things like that. Same again, of course, here between G and then the other end nodes on the very right-hand side. So there is no information flow between all of these nodes, but always between server and a client here. Of course, it can also go quicker, as you can see down here, A to E and then to L, or even just eventually A to an end node L or I or J. Every possible combination here is possible. So let's go back to what we did in the Alliance. Besides creating these application profiles, we also created documentation and testing, certification documentation and testing tools that we need to really prove interoperability and test devices and certify devices. So we have the profile specifications, but we also have the protocol implementation conformance statements, which tells us which features are supported by the devices under test. And then, of course, we have test plan and test tool that members of the Alliance can obtain to do pre-testing or development testing. And the same tool is being used in the test lab to do the certification testing. And then we have a number of other certification documents which are being used to, first of all, track certified products, to post them accurately on our website, and to really make sure that products in the market stay conformed with the OpenADR standard by ways of comparing firmware, for instance, and things like that. So these are the essential tools that we have for the certification and testing, and we did this in order to also satisfy the NIST SGIP and SGTCC requirements to become an ICEA, which is a testing and certification authority for smart grid standards. And the efforts are still ongoing, and we are well on the way to be listed as the ICEA for OpenADR here. So now let's take a quick look at the specification itself. Obviously, we won't have time enough here to go into all the details, but essentially, if you download the specification from our website, you can just go to openadr.org, and there is a resources tab. You will get the released 2.0a specification and a draft B version. You will see that both specifications are set up in the same fashion. So we have an overview that tells you a little bit more about OpenADR. We define the feature sets, and then very important, we have our conformance statements. And that's really what it takes these profiles out of the energy interoperation. So we define exactly how certain mechanisms have to work, and those are also the things that we test. You'll also find information on transport mechanisms, security, and there's also, of course, UMLs, and there are schemas attached as well. We are also looking at a mapping to other smart grid standards. There are certain efforts on the way, SEP2, multi-speak, and others. They are not yet part of the specification, but as soon as they are available, we'll add them there. The protocol implementation conformance statements, PICs, as I mentioned, essentially bridge between the features and the test plan. As I mentioned before, you will have to check off which of the optional items you use, or in fact, for instance, which security and which other features you have built in, and based on that, you need to run your tests for the certification. A test plan, very straightforward, of course, test cases and everything. And we also have some implementers guides that our members have been working on to make it easier for others to really grasp what we're trying to do and how the implementation would work. So now let's go back to maybe a little easier architecture picture here. So as I mentioned before, you saw these A and B and C nodes, basically VTNs and VENs. And this is a simplified view of that. Essentially, at the top end, we have the ISO or utility that has to juggle the different needs out there. And they can talk either to aggregators that can then in turn deploy certain resources, or they can talk directly to commercial, industrial, small, medium businesses, or of course residential installations. What we have seen so far is mostly energy management systems in commercial, industrial, small, medium businesses, and smaller home area management systems, home energy management systems in residential settings. We do also see some companies implementing thermostats that can connect to an OpenADR server, and with that also control, of course, the typical applications like heating and air conditioning in the house. Again, want to mention real quick that these arrows each represent a separate OpenADR link, so there's no networking in place here. We leave all the intelligence up to the entities that are in the middle here, like an aggregator. They can do their stuff and then use OpenADR to communicate the information down to their resources. Now, I mentioned earlier the 2.0A and B profile. So you might wonder what that really means. As I said, the energy interoperation from OASIS is a very large framework, and we wanted to adopt this so that simpler devices like a thermostat, as I just mentioned, can also run DR clients without really completely exhausting their capabilities and go way beyond their memory and other requirements here. So the OpenADR 2.0A profile was really created for these simple implementations, essentially focusing on a simple price information and simple event information. Then the B profile is a much more complete set of functions. That is not to say that a thermostat, in particular one, for instance, with a web GUI or a web-hosted interface, could not handle it, but it's probably fair to assume that energy management systems will use the B profile, as it provides, in addition to a much more granular way of communicating events and prices, it also provides feedback and reporting capabilities for historic data, telemetry data, or even forecast modules. Also, we have built in, for instance, a green button transport system, so that green button data can also be relayed using the report functionality here. we have consciously chosen A and B because we don't know what the future brings us. So there could, of course, be a C or a D profile depending on what the needs are, what feedback we get, what we learn over the next few years. And there could be other country requirements or even under other standard-based requirements that will flow into the next profiles here. So a quick word on the transport protocols. We have, in fact, two specified for the A profile. It's primarily the simple HTTP. That's kind of our pet name for it. In fact, it's really just a simplified REST interface. And we use the standard HTTP command set in there. And we also specify XMPP as a possible transport protocol. For those of you that are not familiar with that, this is, for instance, something that a lot of the instant messenger applications out there use, as well as Facebook and so on, to push messages very quickly to clients without running into, for instance, firewall issues or other communication problems on the way. Reason for choosing this was that we are seeing more and more demand for a very fast automated demand response. In fact, something like 4-second response times for load balancing and things like that are definitely possible. So the XMPP protocol here enables us to really satisfy these systems out there. From a security perspective, we also support two levels of security. What we call standard security is a typical TLS transport layer security with server and client-side certificates. These certificates are being created by CAs that follow our certificate policies. And then we also prescribe a high security mode, which includes the standard security, of course, but it adds XML signatures, so digital signatures, to the messages, in particular to increase non-repudiation where this is necessary. In this case here, our standard security is mandatory for all devices to include, and then the high security is optional. I won't go into these details. I think time is running fast here, but these are some of the programs that we already reviewed and, of course, support. But we will try and create a white paper in the near future to see which programs are easily covered with which OpenADR profile. All right, so I think I give it back to Barry here fairly quickly to go into a little more detail on the Alliance.
Okay, thank you, Rolf.
I am transferring the privilege to you, Barry.
All right.
You should have it now.
Thank you. So what is the OpenADR Alliance? As we've discovered with industry standards, it's very difficult to get standards adopted in industry without having an organization behind them in order to promote the standard and solve some inherent challenges such as device-level interoperability, independent testing and certification, et cetera. So the OpenADR Alliance was really formed to bring the OpenADR standard to market, build the testing and compliance program, and provide a mechanism to propagate the standard worldwide and to help companies building products to the standard to sell and promote those products to utilities and energy providers worldwide. So as you heard from Rolf, we've now successfully implemented a testing and certification program, and I think we've certified 7 or 8 products at this point in time. We as an organization are not creating standards. We're leveraging existing standards and bodies of work from OASIS, from SGIP, UCA, IUG, NASB, and others when necessary. So our goal really is to take those standards and bundle them in a way so that they can really be implemented successfully. And our ultimate goal here is to enable a large stakeholder, multinational stakeholder group to bring the standard to market and get OpenADR widely adopted by utilities and energy providers worldwide. So our mission's pretty simple: foster the global development, adoption, and compliance of open automated demand response standards through collaboration, education, testing, and certification. And we are now that testing and certification is largely completed, we're focusing most of our efforts on education and testing, hence the webinar today. So our goals, 4 simple goals that are the focus of our organization: coordinating with existing standards bodies and organizations, the implementation of testing and certification. We're now focused on getting the 2.0B profile specification completed so we can test and certify products to that. Reaching out and educating industry on the, how to create OpenADR-related programs and really promote global adoption. We have a typical alliance model. In our case, we have sponsor members. These are companies and entities that want to play a strategic role in steering the organization and the standard. We have what are called contributors, which are the vendor class of companies that provide hardware, software products, and services into the marketplace. And we've got adopter members, which are typically utilities, system operators, labs, and universities that have an interest in either using or applying this standard. We're pushing about 100 members worldwide. As you look at our member roster online on our website at openadr.org, you'll see that we have a growing number of companies in Japan and having quite an impact in the Japanese market. So the benefits that this organization brings to industry are pretty straightforward. We're creating a fairly large ecosystem of industry stakeholders to market. We're filling in all the gaps in terms of the types of products and services that are needed to fully deploy OpenADR 2.0. You will start to see a pretty full complement of OpenADR certified products coming out in this summer. You'll see the first products probably in the April-May timeframe. You'll see that with the availability of those 2.0B certified products, that distributed energy resources will start to become quite prevalent in the deployment models. And you'll find that from a deployment standpoint, there will be a nice selection of off-the-shelf products that have OpenADR interfaces built directly into them. For example, building management systems, residential gateways, thermostats, lighting control systems, load control centers, et cetera. And we'll continue to develop tools to propagate this. So in terms of where we've come, we have published the OpenADR 2.0A profile specification that's downloadable on our website. We've built a test tool, some people call it a test harness, that allows products to be certified against that. We are nearing completion of the 2.0B profile. If you want to see a draft of that, you can download a copy from our website at openadr.org. It provides, that B profile provides really the standard set of features that you would need to implement a full OpenADR program within a territory. We are fairly far through the process of getting OpenADR 2.0A and B through the SGIP catalog of standards. I believe we are a candidate for the next vote. We're also working with IEC to get OpenADR established as an international standard. That's an important milestone for us. So we're working with a number of entities to make that occur. And we're investing a significant amount of energy in the Japanese market and have a significant amount of interest in applying OpenADR in Japan. This is just a quick snapshot of some of the products. You'll see that there are right now are 3 servers that have been certified and 4 clients. And again, most of the companies are waiting for the B profile to enter the certification process. So once that profile specification is published and the tools available, you'll see this list grow. If you're interested in monitoring the progress and availability of products, you can see the URL down below, and we encourage you to visit the site. A couple other things worth mentioning. California's Energy Code, Title 24, has a reference to OpenADR in the code that takes place in 2014. And in my interpretation of the code, buildings over 10,000 square feet, new constructed buildings over 10,000 square feet will require a DR interface based on an industry standard, of which OpenADR is the leading standard. So we will see quite a strong pull-through of OpenADR deployments in California, and this also will bring in core manufacturers that will ease the deployment of OpenADR through programs in the rest of the country. It's also now possible to get a LEED credit for OpenADR interface in a building, and it looks like the number of LEED credits for OpenADR will grow in future releases of the USGBC LEED program. So this is a large market opportunity. This is some data from Pike Research forecasting the market for OpenADR through 2018, and we're going from basically 0 today to about 80,000 site installations through 2018. So there's pretty strong growth in the market for OpenADR certified products. So wrapping things up on the OpenADR side of things, what we're doing here are supporting 3 basic tenets. One, we're standardizing the interface for automated demand response, both at the utility head end or the energy provider, but more importantly at the client or the customer interface. So what this means is that OpenADR certified products will be available to support a variety of applications in the residential setting. We're automating that resource so that energy providers can leverage OpenADR to share energy price and event information using the internet in a secure connection. And ultimately, we're simplifying the deployment of DR programs by providing flexibility to utilities and energy providers to implement DR resources and programs that are affordable, rapid, and secure. And with that, I think that's the end of the OpenADR presentation. Thank you.
Great. Thank you, Barry. I think that there are a couple of quick relevant questions that have been posted. You could easily respond to them before we move to the USNAP presentation. And one of the questions is coming about how OpenADR will work, especially in California, where several of the smart meters have Zigbee interfaces and not an IP platform. So you mentioned there's some talk about a gateway. Could you elaborate a little bit on that?
Yeah, so in order for OpenADR to operate, it needs an internet connection. So if you had an IP-based AMI solution, in theory, you could send OpenADR signals through that AMI infrastructure. What we're starting to see actually is the deployment of a parallel network where AMI is really used for what AMI is good at, which is remote meter reads, outage detection, power quality measurements, et cetera. And for DR, using OpenADR as a way to get fast demand response messages to a customer. So there are some energy gateways, universal devices. A member with a certified client product has a device that can take an OpenADR signal and convert it into Smart Energy Profile. I believe there are interfaces for Zigbee and Wi-Fi and other popular standards. We've got a number of other members who are building residential gateways as well as residential thermostats or thermostats for the light commercial market.
Okay, and then the other question was about how the Open ADR Alliance works with the Sun Spec Alliance.
Well, right now there's no collaboration between the two, but there could potentially be an opportunity for collaboration.
Okay, very good. So at this point, what I'll do is just mention to people online that we are going to have a more extended Q&A session after both of these presentations are completed. So feel free to go ahead and put those in the question window. And I'm going to ask Barry now to start the presentation on USNAP. Just one comment before you go ahead, Barry, is that please keep an open mind about this standard. This in no way is trying to replace Smart Energy Profile or all the good work that's going on in that and many other protocols. And Barry will explain as he goes through the presentation on how the architectural flexibility has been kept to adapt to any environment. So with that, Barry?
Thank you, Irfan. So what I'm going to do is introduce Chris Cotting. Chris is the incoming executive director of the USNAP Alliance. He's got a long history in the energy industry and has spent a fair amount of his career on the regulatory side of things. And I'm delighted to have Chris on board to manage the day-to-day operations of USNAP, and so I thought I would throw his feet into the fire and allow him to present the material today. So with that, Irfan, if you could pass the ball to Chris, we'll let him continue.
And
well,
he
thanks,
has
Barry. Thanks, Irfan. And Barry, thank you for throwing me into the deep end of the pool. Let me go ahead and get some things rolling here. As Barry indicated, I actually spent 28 years with the Ohio Public Utilities Commission and finished up my career there, starting to work on infrastructure and smart grid. So that's what I've been doing actually since I left the commission, is pretty much a lot of work on smart grid and standards development. So talking about standards, what in the world do we need another standard for? Aren't there enough of them out there already? This slide, you see on this slide a number of different standards that are in place in the residential space for devices to communicate with each other about operation, about energy usage, about a number of things. And that's exactly the problem. There are over a dozen different communication standards and forms for home automation, energy management, entertainment. And that creates a problem when you start trying to bring either simple demand response or the more complicated things that are envisioned by Open ADR 2.0 and other standards that are out there. In addition, customers want to make their own decisions about the hardware they put in their homes, which means that you're not going to necessarily have customers putting in new appliances just so that they can participate in a demand response tariff or so that they can have a home energy management system in place. So the question is, then what? Every device has its own issues and its own capabilities that can be contributed. But there's no single good way to get them all to communicate even basic information. They all use different platforms for communication. Many of them don't communicate at all as it is. Many of these devices are legacy devices and don't have much in the way of native intelligence. on top of those problems, we've got a lot of different options for demand response. Open ADR, SEP2, some basic DR. You have proprietary AMI deployments out there. You've got demand response signals going over pager, over cellular. You have proposals for pricing information moving over FM sideband or cellular or any of a number of other technologies. So given that, and given that we're looking at systems coming online that go beyond simple demand response to price signals, to intelligent integrated home management, microgrids, the number of possibilities becomes dizzying. So how does a manufacturer produce a consumer product that can be sold anywhere? Or are they stuck with catering to a million different niche markets? In order to enable smart grid-ready products, we have to enable some level of connectivity, some level of commonality. We have to have a way of dealing with any demand response standard. We have to have a way of dealing with any home automation network standard. We have to have a way of dealing with proprietary networks, and we have to have a way of dealing with standards that don't yet exist. Basically, we have to enable connectivity between and among devices in a way that doesn't foreclose technology changes, doesn't require a truck roll for a technology change, and allows manufacturers to produce equipment that both innovates and appeals to customers. So how do you go through that? How do you do that? Well, we kind of looked at an existing, fairly successful industry model. Develop a simple and rugged connector and protocol that meets the current and near-term needs but allows for changing technologies over time. USB does it. Secure digital cards do it. Even the dearly departed PCM-CIA did it reasonably well. The goal is to create simplicity for the user, flexibility for the manufacturer, and extensibility for the future. What you're not actually seeing on this slide is the text, unfortunately. Let me see if I can get the laser pointer cooperating here. What we have here is we have this concept of pluggability. And what we have here is actually a smart grid device, which could be a Wi-Fi router. It could be a thermostat. And what you have is a pluggable module that, just as USB does, allows you to interface a number of different devices over a common specification. Oops. There we go. Ah, that's why you don't see it. So you have the smart grid device. Then you have the universal communications module, universal comms module. And that combination has been standardized now as the ANSI/CEA-2045. I see a question from Chris King. Is this the same as the CEA socket standard announced last week? Yes, it is. This is the 2045 socket that was announced last week. It was actually approved just after Christmas last year was when it voted out. So the concept here is that you've got a universal connector, or actually a couple of different universal connectors, one for DC-based implementations and one for AC-based implementations. But they provide a physical interface to any network, which allows you to move the network hardware off the device and onto a plug-in module and a platform that allows for two different basic forms of operation. You can have any communication system as long as you have the appropriate communication module. For relatively simple devices like older hot water heaters that don't have built-in intelligence or pool pumps or things like that, you can have a simple on-off interface. But in that same module, you also have the pass-through of more elaborate data that allows more intelligent devices to access and use that data and use that module for communications. So the primary characteristics that we have to have in place. There has to be some kind of uniform standard, and we now have that in place. The modules are homeowner installable, removable, and replaceable at any time. Manufacturers can produce smart grid-ready products without having to build in communications or even building in multiple communications. Let's assume a manufacturer wants to build a pool pump that is ready to work with a demand response system. Well, they would have to figure out which demand response system a given utility, which signaling system a given utility was using in their service territory, or which signaling systems were approved by any of the 53 different regulatory jurisdictions in the U.S., let alone those in other places around the planet. That's the problem for manufacturers, is how do you deal with all of these possible signaling systems? Well, this 2045 interface eliminates that problem. You build a device with the 2045 interface, and then customers acquire the necessary module to communicate with the demand response system that they're engaged in. And the cost of actually installing the communications capability doesn't get incurred until the customer actually sees some benefit. It's simple for the most limited of devices, but it's extensible because of the pass-through capability. Basically allowing simple devices to use the module to participate in existing DR programs. It allows for the capture of what is really the low-hanging fruit in the energy management market. But enabling the pass-through of more complex signaling, it provides for technology growth and change. Communication systems can evolve without obsoleting the end device, the appliance, air conditioner, hot water heater. In addition, an MCI, a modular communications interface device, can move from an appliance to appliance as the appliances are replaced if the communications network stays the same. And appliances can move from one service area or home automation network to another simply by swapping out the MCI. It really provides a great deal of flexibility for everyone involved. In addition, there are a number of gateway device implementations that are in place and being developed, but it allows any device to participate in any HAN network so long as the correct MCI is installed. What I'd like to do is kind of talk about some of the different use cases, because I think that going through a progression of use cases will kind of help us see some of the flexibility that it provides. So here you've got a simple demand response scenario. Utility uses a pager or FM sideband or cellular system to do demand response. And there you have a hot water heater that has an appropriate communications module in place. The utility doesn't have to roll a truck when the customer enrolls. The customer doesn't have to hire an electrician to come out. The customer plugs in a simple module and the job's done. It doesn't matter whether it's a hot water heater, an HVAC system, or anything else. Now, if you've got a utility that's using their AMI system to do that same kind of signaling, again, you just need to have the correct type of modules available for hot water heater, air conditioning. Again, here we're still in a simple demand response, but let me go back to the previous scenario. This doesn't even assume that the company has an AMI system in place. So if the utility then upgrades and starts doing their signaling through AMI, and the meter has the appropriate interface, then it can communicate directly with end-use devices that have the communication modules in place. Again, the appliances don't have to change. There's still no truck roll, no electrician involved. If new modules are required, the customer can just plug them in. Let's assume maybe that instead of the utility changing its communication system to an AMI-based system, the customer signs up with a third-party aggregator. Same scenario. The customer's existing appliances don't have to change. All that has to change is the communication modules that interact with the signals coming from the aggregator system, maybe over Wi-Fi, maybe over a broadband router, maybe using SEP2, maybe using almost any interface out there. Once someone makes the communications module, then communications is possible with any device that has the appropriate interface. So now let's imagine that the home gets sold and the new owner wants to sign up with some other service provider that uses yet another communication system. Or they want to install an elaborate home automation network of their own. They can do that. The appliances still don't need to be replaced, just the communications modules. And I keep talking about the fact that the appliances don't have to be replaced. You have to remember that homeowners generally keep appliances for a very, very long time, and often will move them from one residence to another. There we go. Sorry about that. Let's assume now that maybe the new buyer decides they want to go to a full-fledged home automation system, wants to add a number of new devices. Again, the appliances still don't have to be replaced to do it. All that has to be changed out is the communications modules. One of the keys to making this home automation, home energy management, and some of the real facility that is going to need to happen for the future of an intelligent grid where loads can adapt to available generation is to keep the cost of entry for the consumer low. Make it minimal cost in dollars and minimal cost in hassle. And that's what this interface provides. A lot of companies have taken arrows in the back about customer engagement and customer empowerment. It's unfortunate, but it is true. Well, here's the thing. Here we have an interface that is customer installable, will work anywhere, will work in anything. The utility does not get tied up with stranded assets, and neither does the customer. This interface, the standard, will drive competition and innovation. It enables standards evolution. It leverages the existing consumer models, and it is a model and an interface that should still be viable in 20 or 30 years. Again, eliminating the stranded assets problem. And now I'm going to turn it back over to Barry Haaser so that he can kind of fill people in on some of the evolution. How did we get here? Erfund, if you can, oh, I see you already did pass the ball to Barry. Thanks much.
Sure thing. Go ahead, Barry.
Yeah, thank you, Chris. Just a brief background here. The original body of work for this whole MCI concept emerged through a research project funded by the California Energy Commission. That body of work became public domain in the form of a reference design, and was implemented by Radio Thermostat Company of America. The USNAP Alliance was formed to take that basic specification from Radio Thermostat, standardize it in such a way so that companies could, like Radio Thermostat, could focus on what they do best, which is building thermostats, and we could build an ecosystem of companies that built modules, plastics, and other products based on the specification. So we developed the specification, and then there was a parallel effort underway by EPRI, who was defining a modular interface. We merged those two based on some combined work through the home-to-grid DUG within NIST, SGIP. That final document then became the foundation for the CEA standardization process, and resulted in the standard that CEA and EPRI announced last week. Now, EPRI has turned its sights on implementing the 2045 standard in a variety of consumer products, and before long we'll hear about a number of projects that EPRI is leading with their utility partners to implement the 2045 for a variety of DR-related applications. Sorry, I didn't realize this was a build. There we go. So I think I talked about this already. The combined USNAP and EPRI effort through NIST resulted in the CEA standard, and since this is a CEA standard, in order to obtain a copy, you need to visit their distributor, techstreet.com. I believe they're charging $145 for the specification. We, the Alliance, don't have rights to redistribute the specification, but we will be publishing an abstract of that specification very soon on the website at usnap.org. So if we look at what EPRI's been doing here, they have hosted a number of workshops with their utility partners to demonstrate the capabilities of the modular communication interface in a variety of consumer products, such as electric vehicle charging stations, electric water heaters, heating, ventilation, to air conditioning equipment, mainly air conditioners, a variety of home area network gateways, load switches, pool pumps, in-home displays, thermostats, and through that, they've been able to test the communication interface using a variety of communication technologies, such as VHF wireless, FM radios, which are popular for AC cycling programs, 900 megahertz mesh AMI, some cellular communications, voltage sensing, Wi-Fi. I know there have been also some Zigbee implementations, which I see is missing from this slide. So there really aren't any limits in terms of how the modular communication interface can communicate or the types of products in which it can connect to. So it really helps bridge all these disparate interfaces into the home, providing utilities with a variety of solutions that they can take and deploy. And as Chris mentioned earlier, the beauty is, from a manufacturer standpoint, they can build smart grid ready products today, not encumber them with communication interfaces, and allow the interface to be installed either by a representative of the company, the utility, or ultimately the consumer. So we formed the USNAP Alliance several years ago in order to cultivate this whole concept of modular communications. There are about 40 members in the Alliance. We're a typical Alliance business model funded by member dues. We are now focusing our attention, now that the standard is complete, on implementing a testing and certification program and branding program. And it's our goal to try and have this program up and running before the end of this year. So as a group, and for companies that are interested in getting engaged, we're looking for companies and people who are interested in contributing to their thought leadership to the certification process. And then those companies that are planning to implement the standard, we encourage you to join to help promote your products in the marketplace. And with that, I'm going to turn it over to Rolf Bienert, who's now going to walk you through some of the technical attributes of the standard.
Excellent. Thank you, Barry. So I'm trying to stay within the time limits here. But I did see a couple of very interesting questions already in the Q&A box here. I believe Barry already answered some of them, but I'll try to also talk about some of these items in the few slides that I have here about it. So looking at the interface itself, and this is a fairly rudimentary picture here, but as you can see, the interface sits essentially between any kind of communication system and the smart grid device. So the smart grid device, of course, can be an appliance, an HVAC thermostat, solar systems, pools, things like that. Pretty much anything that can be controlled. We have, in fact, seen a bunch of trials going on with water heaters, and that's why you see a lot of these water heater pictures in the previous slides. So the easiest way to describe this interface here, this socket interface, I always like to use the old PCM-CIA card system that Chris already mentioned. Essentially, it is an open interface that lets you transfer for certain functionality, certain data, without really knowing what the module itself is actually doing. So in this interface here, we have two different types. One, what we call is the AC version, which operates on line voltage. And the other one is the correspondingly a DC version, which operates on low voltage. That's the one you saw earlier in this picture of the radio thermostat. And it's a much smaller module, of course, than the one that uses the line voltage. So the app layer, link layer, and file layer between these modules are defined in the USNAP and now, of course, also in the CEA-2045 specification. And we use RS-485 for the AC unit and the SPI for the low voltage, the DC version of it. Then in the module, and I'll talk a little bit more about the architecture in a minute here, we can have either a pass-through or DR application set up. And then, as it was already mentioned several times now, really the idea is that the module can receive any kind of signals, smart energy profile, Open ADR and climate talk on a profile side, but then also AMI, home area network traffic, cellular data, Wi-Fi, ZigBee, anything, any other transport mechanisms here to get the data to the module. So let me quickly move forward here. So in a slightly different representation here, so everything that's green in here is essentially covered in CEA-2045. And just to repeat again what I believe Barry mentioned already, so the USNAP specification used to contain what we now call the DC version, the DC module, if you will. And from EPRI, we get the AC system, and we combined this within the work of the NIST groups, and then we refined all of this in 2045. So I see a bunch of questions popping up how 2045 fits into this here. And yes, in fact, it is the 2045 that you might have seen in a press release just a couple of days ago. And so the spec contains everything that's in these green boxes here, so that the physical connection, data link layer stuff. And then we define a basic intermediate demand response application command sets, if you will, on the application side. And secondly, we also define a pass-through mechanism, and I'll talk about these architectures in just a minute here. So to make this a little more clear, I've extracted some of the graphics from the 2045 specification here, so you get a better idea on how this stuff looks like. So on the lower left side here, essentially you see the DC module and also the DC connector on the very left side here on the bottom. The DC connector is in fact a standard micro SATA connector that manufacturers can purchase from several sources. We mentioned here TE because they helped us get all of this started and adjusted and implemented, because that's really the biggest physical change from USNAP 2 to CEA-2045. This connector is now much more solid than the old pin connection. So these are sliding fingers. They will not bend or anything like that, even if the end user might to an extent abuse the modules, and even if you pop them in and out, they should pretty much stay in place. And they have additional guide posts and rails, so that it's really difficult to mount the module wrong at the end of the day here. Then the scale is not quite right here, but on the right-hand side as well as on the top left, you see the AC module. So really the AC module is quite a bit larger than the DC module. That's not quite reflected here, but we couldn't fit much more on the slide. So we have minimum space requirements lined out in the specification. So an appliance must have a minimum space allocated for the AC module, if they can receive one, that is about as big as this top view that you see here. But the module, of course, can be smaller. I mean, it only has to accommodate the connector, which is depicted on the top left here, as well as the two screws that are shown here as black dots. So we also, in fact, added these screws pretty much in the end of the CEA-2045 standardization process, because we didn't want any of these modules to pop off, say, a washer or dryer when it starts vibrating and shaking and things like that. So these screws were added here. As you can see on top left, this is the connector with a little pin layout. Pretty straightforward, and it can take either 120 or 240 volts in one line, or it can actually take two line voltages with so 220, 240 volts, as you can see here, line 1 and line 2, to operate the module. Of course, manufacturers must then take care of applicable UL requirements if you're feeding line voltage into a module. Of course, there's other isolation needed than if you have DC going into it. So, as I mentioned, a quick review again of these architectures that we have seen. So, you can either terminate the smart grid protocol within the module. So that would mean you have, for instance, SEP2, or you have OpenADR, or other standards that are out there coming to the smart grid device, and in fact the module itself, the MCI, represents, say, like an SEP node or an OpenADR client, and terminates that communication signal within that module, and then it communicates using basic DR messages or additional intermediate DR application messages with the smart grid device. So your water heater, for instance, will probably not have a lot of intelligence, so basic DR messages like shed now, turn on, turn off, things like that are probably the most applicable for these kind of applications. Whereas if you talk about other devices, maybe even refrigerators or other systems that are much more intelligent, you could potentially have, of course, additional messages being exchanged there. But again, the key is that these smart grid technologies terminate in the module. Now, on the other hand, you have the smart grid protocol pass-through. In this case, the module really just acts as a physical layer bridge. In order to be certified, a USNAP 2045 module, you would still need to be able to support basic DR messages, but you could switch into a pass-through mode where the module itself just terminates the physical layer and passes on whichever smart grid protocol, again, SGIP, OpenADR, to name a few, it passes those messages unaltered on to the smart grid device. What that means for the smart grid device is that it needs to implement, say, like an SGIP, SGIP1, SGIP2, whatever is applicable for the unit, or even other standards. But maybe to stick with SGIP, it would then be conceivable, for instance, that you terminate your SGIP2 link in the smart grid device, but you do not add, say, like ZigBee and the Wi-Fi and the PLC communication radio and system to it. You would leave that to the communication module to provide you with this connectivity. So whether a household has then a Wi-Fi SGIP2 network, they would just use a Wi-Fi physical layer unit, and vice versa on ZigBee or on PLC and things like that. So that is the second architecture that is supported by the module. And we have seen so far several manufacturers, looking at both kinds of architectures to realize their products out there. So I hope that somewhat answers a few of the questions that I've seen so far. Then real quick, automated slide. I also saw a few questions again on this 2045. So we had this update in here. The CEA R7.8 committee, it's a subcommittee to R7, which is home networking, looks at modular communications interface for energy management. And there is the R7.8 working group 1, which is essentially the technical working group that worked on the specification. We modified a lot of little things that were in there. Nothing really major after the merger of the EPRI and USNAP specifications, but we found a few inconsistencies and other things. As I mentioned, of course, the connector issue was taken care of, in fact, for both DC and AC modules. I'm the chair of that working group, so feel free to ping me if you want to know what's next for the group and so on. The CEA 2045 was then passed by the committee. The vote closed, in fact, on December 24th. Interesting date to pick. And then went on through the ANSI approval process within CEA. And happy to report that it is now available as an ANSI CEA 2045 specification and standard. I included the link here. If you go to this website, you have to scroll down to CEA R7.8. And from there you will find some links to preview the document or to purchase the document. And so next steps for the CEA committee are certainly to look at any additional features for future versions. We have some ideas already that we'll discuss with the CEA committee pretty soon. And we are also, for instance, thinking about a smaller version of the DC module, the one, in fact, you see here on the top right. This is, by the way, the old connector here, not the new one yet. But we're thinking about a smaller version of that, since obviously chipsets have been shrinking over the last few years, in fact tremendously shrinking. And we look at a concept like, for instance, SD cards and micro SD cards, where one would fit into the other to keep backwards compatibility with newer models and things like that. And as it was mentioned multiple times, the USNAP Alliance has started talking to test houses and test tool providers, and we're starting the process to create a certification program. So if you are interested in being a part of that and would like to have some say on these modules, definitely ping Chris, Barry, or me, and we'll see how you can get started with that. All right. I think do this quick summary as well here, so we don't have to swap back to anybody else. I think most of it was already said, but really the key is that there are a lot of standards, and we thought it would be great to have this uniform communication interface standard that can combine all of these great systems out there. And these modules are easily installable by the homeowner and replaceable and things like that. And manufacturers would not incur really large upfront cost by implementing several radios or even several smart grid protocols, but rather, in particular for simple devices, just implement the interface with a simple command set. And that will also enable, of course, then the simple devices to install this and yet be able to extend to additional functionality later. And last but not least, of course, we want to avoid stranded assets. So we need to make sure that we can evolve all these smart grid standards without really the need to buy new appliances, new systems, new pool pumps, and other smart grid devices like gateways and things like that in the future. That being said, I believe that was the last slide. Yes, so I think we'll pass it on back to Irfan for the Q&A.
All right, very good. Thank you, all three of you, for a very informative set of presentations and addressing a lot of the issues that people are discussing in the industry regarding both of these standards. One question that I have before we get into the ones online is that we've seen, for instance, with electric vehicles, there's pushback on having a standardized location for batteries that can be pulled in and out. And I know that Better Place has one solution like that. And a lot of the car manufacturers are saying there's an optimal place to put the battery, and it's not so easy to take it in and out if you put it there. So the question then arises on USNAP also, that a lot of appliance manufacturers like to place the communication in a particular location based on whether it's RF or it's power line carrier, and there are issues about RF shielding, there are issues about protrusions from the appliance in a real environment like a household. So the question is, how are you addressing that issue of design with a standardized interface like this? Any of the three of you could answer this question.
Sorry, I was sitting here talking to myself on mute. This is Barry. So, very good question. At this point, obviously it's outside the scope of the specification, but is a body of work that would be captured by the USNAP Alliance as companies focus on implementation and creating implementation guidelines and industry best practices. So the way we would approach it would be to assemble a group of people interested in addressing those problems, and then publishing our recommendations.
Yeah, so one recommendation I would make to your group is to document some use cases and use that approach to explain how your specification will be addressed, how the use case will be supported by the specification, so that you can provide some guidelines to the manufacturers, because it would be unfortunate to put it somewhere where, okay, it works from a communication perspective, but not practically.
Yeah, very good observation.
Okay, so at this point we will go to the questions and there were several questions that were asked, and Barry, I saw you were responding to them. So what I would suggest is that you scroll down these questions and see if there were ones that you have not addressed, and feel free to lead it with Rolf and Chris supporting you.
Here I am talking with my mute on. This is Chris Cotting. There's a question from David Erickson. Current DR systems I'm familiar with use an RF signal to do direct load control. Utility provides the RF signal. How would this best be replaced by an OpenADR USNAP solution? Well, I can't speak to the OpenADR aspect of it, but the USNAP aspect is that depending upon how the utility sent that RF signal, you would have a USNAP module that actually received that signal and passed it on to the device, either in the form of an actual on-off command for a simple DR scenario, or in a more elaborate scenario in the form of a pass-through instruction. And I'll let Barry or Rolf talk about the OpenADR part.
Yeah, I think I'll go ahead and read the question, and if it's been answered, go ahead and say it's been answered. The next question is, we talked about what is the largest scale that has been implemented for OpenADR, and Barry, you responded by saying you believe it was around 120 megawatts. So a lot of times these questions are asked, but the public, everyone else online may not have read the answer. So I'd like to record it on the audio. And then the next question from Dave Erickson says, Barry, are you saying that OpenADR probably will be used in parallel over an IP-based network or the internet rather than interoperating with the utility AMI home area network? I believe you made the comment about the parallel architecture. I think Rolf also mentioned that. So I think that's been answered. And then the next question is, Dave says, I'm asking, okay, that's fine. The next question from William Miller says, how does OpenADR work with the Sun Spec Alliance? And the answer was that there isn't a working relationship yet. And then the next question was from Franz Gorges, who says, what new features will we see in 2.0 compared to the existing 1.0? So Rolf, do you want to take that?
Yes, I can jump in on that real quick. So the 1.0, was primarily used for simple signals. So most of the implementations out there use just 4 simple levels, and that's very close to what, for instance, our 2.0a specification does as well. There was a provision in 1.0 to also do more complex things, but it wasn't really used a whole lot. So beyond that, now in 2.0, OpenADR 2.0, in particular B, we defined much more granular ways of defining events, signal types. We support, for instance, also direct load control. While we do not really control devices, that's not our domain. That's, for instance, SEP, CP2, and things like that. We don't control these devices, but we do enable direct load control programs by sending, for instance, signals that are specific, that can be, I should say, specific to certain device types. Then in addition to that, we of course also have the reporting mechanism that I mentioned earlier. So the whole feedback loop has been added to this, and we have also additional registration and opt-in, opt-out scheduling functionalities. So there is a lot of additional stuff, but I think main changes are probably reporting feedback, a very specific transport protocol usage, and additional security.
Okay, so the next question from Srini is, can the MCI be expanded to process the application based on prevailing standard like OpenADR, SEP 2.0, and pass signal to the SGD in its native format? I think you've answered that question already.
I believe so, yeah. Those were the two different architectures that
yes.
that we see here.
Okay, very good. And then the next question is from Phil Davis, who says, do you happen to know if Ecofactor can use OADR for its thermostat cloud control function? And I believe Barry answered that, saying that they are a member, so the assumption is that they support it. Okay. Then Slav asked, could you please post a presentation record? Okay, I will do that. I will be sending the presentation to everyone in the distribution, and including the webcast recording. And then the next question is, well, then Chris King asked the question about whether this is the same as the standard that was announced in the CEA conference, and the answer was yes. And then Jeff Mulligan asked, isn't USNAP only one of the protocols that is accommodated by the MCI, so USNAP is not the same as 2045? I believe you answered that in the presentation, showing how the EPRI part and the USNAP part came together, went into the PAP, and then was defined as a standard, right?
Yes, I think so.
Okay, so I think we're good there. And then Dave Erickson says, these communication modules basically convert everything to OpenADR, and all the appliances and so forth speak OpenADR. So
I think there's a bit of a mix-up.
I think so, yeah.
Yeah, we probably cleared that up, I would think, in the last part of the presentation.
Okay. So, yeah, two different presentations, and the USNAP is independent of the signals that are coming. The appropriate modules can interpret that signal and give it to the USNAP interface in a way that's meaningful to it. And there are two modes. Either it's the basic primitive instructions that it understands, or it passes it through. Okay, so I think we're good there. Chris, okay, then I see some answers here. Then Catherine Tweed asked, could MCI modules someday be OpenADR 2.0 devices, or is the MCI module only intended for more simple demand response programs with one-way communication?
Yeah, I think it was also at the end of the presentation. I tried to answer a lot of these questions that I saw, but yes, absolutely. I mean, the idea would be that these modules are full OpenADR devices in a sense, or even SEP2 or others, whatever the protocol is.
Right, so depending on the sophistication of the end appliance, it can either receive the more complex, in which the module is just passed through, or some basic instruction of DR is given, which the appliance can understand.
Yep.
Okay, and then Costas says, could you provide further info about CEA-2045, any document? I think, Barry, you answered that by having them go to the CEA website, becoming a member, and getting the thing?
Well, actually, that's a public page.
Ah, okay.
Yes, let me just go back to that real quick.
I think you gave a website in your response, Barry.
Yes.
Right.
And then, so right here, this is a public website, and you can purchase the standard for a small document fee. That's
okay.
That's the way CEA does that.
All right, very good. And then Graham asked, do you see OpenADR 2.0 be helping facilitate the aggregation and bidding of regulation services to PGM as presently happens over a proprietary network? Barry, you want to
Yeah, so the vision is to be able to support bidding in the future. Right now, the B profile does not support the bidding capability, but that was part of the thinking of the ABC naming convention. Was when we originally created the C category, it was designed specifically for the ISO RTO aggregator model of which that would fall into. Now, after some work sponsored by the IRC, the ISO RTO Council, through PAP 19, they concluded that most of their requirements were supported through the B profile, but the bidding portion was not, to the best of my knowledge, wasn't addressed in that PAP.
Okay, and then Farshad Samimi asks, how do you compare OpenADR versus SEP at an end node? Example, between an interface module and a load control switch.
Yeah, so maybe I'll start. We of course get that question quite frequently. I mean, from my personal view is always that SEP, ZigBee, and these systems, they're command and control networks. So they're doing load control. They can control all kinds of devices out there. They form a home area network and things like that. OpenADR really just brings you the information that you need to realize your strategies in the facility. So from our viewpoint, we see OpenADR as the protocol that brings the demand response information, whether this is event or price or other things, to a facility or building, and then within the building, for instance, SEP2 would take over, maybe even connect also to the meter to gather some meter data and things like that, and then control the devices in the facility, in the house, to act upon the signals that they receive.
Yeah, and this is a very good example of how there's been scope creep of standards. Vendors are trying as much as possible to provide an end-to-end solution, so protocols that were meant for home area networks are slowly creeping upstream and going into aggregators and other places. I think it's important with presentations like this to understand the scope of each standard. Where is it best used? And then define boundaries where they're meaningful, as opposed to just letting things creep beyond their relevance. Okay. So moving along, we have a question from Franz who asks, will we be able to extract meter data? And I believe the answer was that OpenADR is not designed to extract meter data, but it does have support for green button data. Okay?
Yeah, and I wanted to quickly maybe mention in addition to that, so like we said, I mean, we do green button and we also provide reporting functionality. So if meter data is available in, for instance, an OpenADR gateway device, then we can report that back to the utility. But we are not meant to collect meter data, for billing purposes. I mean, I don't know if any programs would like to do that, but that is really not the intention of OpenADR.
Yeah, and I think that this is an area where the harmonization between the smart energy profile and the common information model is going to be very helpful, because that's the kind of standard that is used on the back end for this detailed analysis on energy and developing analytics on that. So I think it's important to, again, look at each standard and see its relevance. What is it primarily there for? So OpenADR is about enabling demand response applications, creating a standardized interface amongst multiple stakeholders, because this has been a real challenge with each group doing things in a proprietary manner. So having an open standard interface, and in a way, thematically, I really like the fact that OpenADR and USNAP were presented in the same webinar, because they're both trying to address similar issues about creating standards. Keep the picture simple, provide the basic thing that gets the job done. Don't try to complicate it too much by making it too heavy and so that it becomes obsolete quickly. And I think both OpenADR and USNAP are both trying to address that issue. Very good. All right, moving along, we have George Kutitas, who says the communication module is going to be an IPv6 interface or an interface to an already existing HAN. I think we have addressed this issue. that with OpenADR, it's on an IP platform. So meters that have IP platform, they can support it, and there's a parallel network that can come over the internet that can also support it through some kind of a gateway. All right. Next question is Mark Borens, who asked, wouldn't that language need updating over time, and hence the appliance will need updating to understand the new language? This is about USNAP and about how, there'll be future support. So I think you've addressed that issue also by talking about pass-through and about the basic instruction architecture.
Yeah, I think the thing that has to be remembered is that USNAP enables communication. If you have communication and you have to do update in terms of software protocols, you can do firmware. Right.
And the key thing is about the pass-through is that it makes it relevant for the level of sophistication that the device is. It doesn't mean that you're going to continue passing through more sophisticated protocols to a device that doesn't understand it. It just means that future devices can have pass-through with more complex messages sent to it, not for the same device. I think there was a little confusion about that. Okay. And then Chris Terrell says, which home appliance and device manufacturers are participating in the EPRI interoperability, and are any manufacturers selling end devices in the market yet? I think on the EPRI part, you didn't mention them by name, but then you showed a whole set of vendors who are involved in the alliance, correct?
No, we didn't share any vendor information today.
Right, but you did talk about the alliance, that the larger group of people who are part of USNAP.
We did, but we did not list the members in the alliance today.
Okay.
Yeah, at this point, there are a number of, shall we say, the usual suspects who are working on them, but it's a little too early to name names.
Okay, very good. And when you are in a position to name them, what would be the forum in which you will announce them?
Well, I mean, as soon as we see some once we're able to test and certify products, obviously we'll promote those. I believe that as the EPRI projects mature, they'll probably start releasing public information on the projects and the project participants.
Okay, very good. And then next question is there a need for protocol conversion on the appliance side if it uses the USNAP approach? And the answer, I don't think, only when you're converting to the basic message, right? The pass-through doesn't require that.
Yeah, if I understand the question correctly, yeah, that's correct. Yeah, I mean, you would convert basically. I mean, as said, I mean, you would terminate. You would represent, say, like an SEP or an OpenADR node in the module, and then the module needs to convert that into like very simple commands for the basic DR messages to the smart grid device.
Yes, I'm really glad that you kept your abbreviation limited to MCI and not take it all the way to WorldCom. All right. So next question is Ray Hayes is asking, CEA-2045 requires the appliance manufacturer to expose the socket interface, provide an internal protocol to touch the socket and control hardware. How many have done that to date? So because you're not mentioning their names, can you mention numbers?
Yeah, I believe with the current specification, I think there are about a dozen companies that have either implemented or in the various phases of implementation today, most of which are participating in the various EPRI projects.
Very good. Next question is, Dave Erickson asks, current DR systems I'm familiar with use an RF signal to do direct load control. Utility provides RF signal. How would this be best replaced by an OpenADR USNAP solution? I don't think it needs to be replaced. I mean, it can work because the module will have the RF antenna on it, right?
Yeah, the USNAP module will provide the RF, the receiving end of the RF communication.
That's correct. Okay. So next question is Dale Gutierrez asks, is a possible hand migration a different band like the now functioning 60 gigahertz band or 802.11 AD under review?
Possible. I'm trying to find the question.
I'm not sure I understand.
I don't understand. Yeah. I think that he's talking about moving from the 900 megahertz or the 2.4 gigahertz.
Well, I think he's talking about the new super fast Wi-Fi as well. So yeah, I mean, essentially there would be also just another module required to do that, but
yeah.
I don't know how they would play right now with say like a SEP2 or other system.
I think the key thing to remember here is that as you go higher in frequency, the propagation becomes more optical-like, and that you will have more of the issues of fading, with multiple reflections and things like that. You will get enhanced bandwidth, but with simple commands, it's not really a bandwidth issue. So there is a sweet spot in frequencies that you want to use in home area network. Okay, next question is William Miller asks, scale questions was related to number of actual devices. So is there an issue about how many devices a USNAP module will support? Well, that's a one-to-one, but how many modules could you have in a home speaking, let's say, to a meter or to a gateway?
Depends on the capabilities of the meter or the gateway.
Okay, yeah, so that's protocol dependent on how many nodes it'll support.
Right, it's protocol dependent, and we have in SPI and the other communication protocols, we have an addressing scheme. For instance, if you have a gateway device that has multiple ports, you can address these ports individually, of course. So there's an addressing scheme for that. But I mean, I doubt somebody would build a gateway that has 16 or more ports. That would probably be useless.
Okay, so the next question is XMPP request response message formats defined in 2.0b of OpenADR?
Yes, it is. In fact, you will see some high-level definitions also in the A specification. We just haven't had anybody implementing it, so it's in there as a draft section. In B, it will be finalized, and we're in fact just making a few little adjustments. But XMPP is very well defined in some RFCs out there. But yes, again, it's in the specification.
Very good. This question was asked by William Miller, who's quite active in promoting this XMPP standard for sensors and actuators in the electric sector. Farshad Samimi asks, how do you compare OpenADR versus SEP at an end node? I think we answered that question. And the next question, are you specifying compression in the transport stream? So this is for OpenADR.
Yeah, right now we are not looking at compression in the transport, but the notion of EXI compression has been brought up. So we have, in fact, one or two members currently experimenting with EXI, and we're trying to determine whether it really actually helps some. The OpenADR messages by themselves are not that big compared to other internet traffic these days. And while they are bigger than, say, like an SEP1 message, they're still like way below anything that standard internet applications could handle easily. So we're really trying to determine whether it makes sense to have EXI as an optional compression method.
Okay. Next question is, are OpenADR devices registered with a central authority?
Yes, I say yes, because the OpenADR security certificates are registered. So the devices themselves are not necessarily all registered, but the way we distribute security certificates is through a central distribution node that is managed by the Alliance together with a vendor. And any certificate authority, any CA out there can essentially become part of the program by implementing the certificate policies and then going through an audit to be part of the OpenADR security certificate system. So with that in mind, all these certificates are registered then, of course. So not each device per se, but the security certificate is.
Okay, I'm just going to take these last two questions and then I have to wrap it up because we've gone 20 minutes over our time. So I apologize to the people online, but I wanted to complete these questions so that a future recording viewing would have all these questions addressed. They're very, very important, relevant questions, so I didn't want to miss any. The next question is, when will 2.0b be out? And I think you mentioned that in your final slide, but go ahead, Rolf.
Yeah, so we're right in the middle of our test events right now for the B profile. We do that to ensure a reasonable level of interoperability. And the plan is to publish a final version of the B profile in the second week of March. And we will then continue our test events, probably in the April-May timeframe. We will see the first devices popping up, and the test suite will be ready, and some final changes will probably be done to the spec then. But you can look in March. You can look for a new version of it on the website.
Very good. And the last question is, the identification of the devices are using a UUID or just the IP address?
Generally, it's just IP address. I have to apologize, I'm not a security expert, so obviously we have the security certificates in there that convert, certain addresses, into parts of the cert and things like that. But the programs themselves, they identify the VENs by their VEN ID, so the servers in programs will provide certain ID numbers to the clients out there. That's their primary way of addressing these devices, basically. But I think William probably has some more detailed things in mind on the XMPP side, so feel free to shoot me an email. Okay,
very good. So I think that this is fine as far as the questions are concerned, so we will stop here on the questions. One thing I first want to thank all three of you for presenting and answering the questions. Our next seminar and webinar joint, which will be presented out of the IBM Innovation Center in Foster City, California, Jerry Ramey is going to be presenting on reliability threats to smart grid communications. And please look out for the announcement on that. It will occur on February 27th, which is a Wednesday, and it will be at 6 p.m. Pacific time for an hour and a half. And there will be a seminar occurring simultaneously in Foster City, California at the IBM Innovation Center. And then also what I want to do is have you pay attention to this Cyter Energy Academy that you see on the page now in front of you. What we are doing is topics like home area network protocols, like the different standards for demand response and distribution grid management, transmission issues, and also regulatory business process issues. We have created a set of workshops, which is the third leg of the Smart Grid Educational Series. So if you think of the first level being the webinars, on the one that we are on now, the seminars is the next one, which is what we're doing at IBM. And then we are offering on-site workshops with industry leaders who are working in these standards bodies to come and teach you things on-site. It could be at a utility, it could be at a vendor, it could be at a regulatory organization, or it could be at any organization really that wants to come up to speed on it. and we're offering these. It's very good. I would like you to reach out to me, and I can provide you the topics that we're covering. It's quite diverse, and this is the third leg, as I said, of our educational series. But that will be for a fee. The first two, the webinar and seminar, are, of course, free of charge. So I'm really, really excited about this academic forum because through this forum, we are getting people like Chris, like Barry, like Rolf, and many, many others who have in the past year presented, shared their views, and gotten very good exchange in the industry. So any final comments, Rolf, Barry, or Chris?
Just thanks much for hosting.
Yeah, thank you, Irfan, and for those of you who carved out some time out of their days today for listening to two important emerging standards. We really appreciate your time.
Yes, and thank you very much. We had over 138 people today at the peak, and I'm really, really delighted to see that these standards are maturing in the way they are, and this will break barriers. This is going to make demand response and energy management become the mainstay, because as we move to distributed energy resources, as we move to what we call the virtual power plant, it is becoming more and more important for us to tailor the demand for electricity to follow the supply of energy. We don't have the luxury of having a lot of excess capacity in the future. And the demand is becoming more and more peaked, and especially as electric vehicles and other electronic goods come into the home, the need to shape them will be more and more, which means more devices need to participate. So on the one hand, on the macro side, we've got OpenADR trying to create that standardized interface for communicating between the various stakeholders for quick delivery of the demand response signal to homes, businesses, and factories. And then on the home area network side, and the light commercial area, having appliances, having modules that can quickly connect and participate in energy management services. I think this is really important. It's not a luxury. It's not a nice to have. This will be an absolute necessity going forward. So thank you all for participating, and thank you again, presenters. And at this point, I'm going to end the recording and bring this webinar to a close.